This example is hopefully helping with understanding or exercising a steady-state sinusoidal circuit analysis for a passive, in this case RL circuit. A simple RL circuit is given here with a voltage source in the form of 50 times sine of omega t plus phi volt, and then we have a simple series of an ideal inductor L with a value of 2 Henry, and we have a resistor in series with a value of 2 ohm. This can be modeled as the effective resistor with a non-ideal inductor, and then we have another resistor of a value of 2 ohm. With this circuit given in sinusoidal steady state, we want to find the value of angular frequency omega in radian per second such that the phase difference between the phasor representation of V1 shown this way and phasor representation of V2 shown this way is just pi over 3 or radian or 60 degree. Okay, to do that we just go ahead with a simple voltage division between this overall impedance and this impedance to find V1 and V2, and then we find the phase difference between these two phasors. So for the record, Vs represented in phasor format would be 50, which is the amplitude. Phase of sinusoid, if it was a cosine, you would say directly is phase phi. Now it's sinusoid, so it would be phase 90 plus phi. We won't be using this, we won't need to use this, but this is just information. So for V1 as a phasor, we are just saying, okay, it's a voltage divider between these two series impedance. One impedance is this set, and another impedance is this one. So for V1, we would just say it's a voltage divider of Vs across these two guys for this total impedance. So it's just JL omega, which is 2J omega for this impedance plus 2. So 2J omega plus 2 divided by the sum of the whole series impedance, which is 2J omega plus 2 plus 2 plus 4 times Vs in phasor representation. No need to compute, but just to say that, let's say this phasor would have an amplitude A1, and let's say it has a phase of phi1. So effectively, it is a representation of phasor representation of A1 e to the j omega t plus phi1. That's the meaning of this phasor. Effectively, signal V1 would be in this format, the real part of this guy. Now for V2, we also have the same idea. So we continue with the voltage divider. This time the numerator is just 2, because V2 is just across the 2 ohm resistor, divided by the same denominator here, which is the total series resistance or impedance. Okay. And same idea. Effectively, V2 phasor V2 is representing an amplitude A2 and a phase phi2, and it's a representation of a complex format signal in the form of A2 e to the j omega t plus phi2. That's the meaning of this. Now, when we are talking about the phase difference between these two phasors, we are talking about phi1 minus phi2. So what we are interested in, phi1 minus phi2, effectively, if we do divide A1 e to the j omega t plus phi1 divide by A2 e to the j omega t plus phi2, so we end up with A1 divided by A2, and then we end up with e to the j phi1 minus phi2. Okay, so effectively, if we divide V1 by V2 and we get this, then the phase of outcome is exactly what we are interested in. So what I'm trying to say is the phase of dividing these two phasors gives us the answer. And it is supposed to be pi over 3 as it is given in the problem. So I'm just going to divide these two guys. So dividing V1 by V2, and the denominator goes away, so we have 2j omega plus 2 divided by 2, Vs cancel out with Vs, so it becomes just j omega plus 1. Alright, I just need to find the phase of this guy, so it means the phase of this thing. So by this we mean the phase of V1 minus phase of V2. This is not the correct representation. It should be phase of V1 minus phase of V2, which is effectively phase of V1 divided by V2. So be careful about this. So this means it is the phase of j omega plus 1, and the phase of j omega plus 1 is just arctan of omega, which should be equal to pi over 3 as the question is asking for. In order to satisfy this, that means a tan of omega is equal to pi over 3, so it means omega is just tangent of pi over 3. So it means omega is just square root of 3 radian per second, or about 1.7. That's it. So hopefully this serves as a good simple exercise to understand steady state sinusoidal phasor analysis for a simple passive circuit.